Let us now start the discussion on module 2 of chapter 4. In the first module, we have already defined two general notions of convergence. One was convergence almost everywhere and another was convergence in measure. Let us recall particularly the definition of convergence in measure. A sequence fn of measurable functions is said to converge in measure to another measurable function f if for any epsilon greater than 0, mu of collection of all x where mod fn x minus fx is greater or equal to epsilon tends to 0 as n tends to infinity. In the last result of the first module, we have proved that if fn converges to f in measure and f equal to g almost everywhere, then fn also converges to g in measure. We start this module with another result in this line. We start with this theorem. If fn converges to f in measure and at the same time fn converges to g in measure, then the limit functions f and g will again be related in the same way, that f will be equal to g almost everywhere. So, the situation is again same as the notion of almost everywhere convergence. Let us look at the proof. If fn converges to f in measure and fn converges to g in measure, then for any epsilon greater than 0, let us write a epsilon as the set of all those points x where mod fx minus gx is greater or equal to epsilon. Now, observe that the set A epsilon is subset of collection of all x where mod fn x minus fx is greater or equal to epsilon by 2 union collection of all x for which mod fn x minus gx is greater or equal to epsilon by 2. This follows from the triangle inequality that mod fx minus gx is greater or equal to mod fn x minus fx plus mod fn x minus gx. Since the sum of the two terms is greater or equal to epsilon, so at least one of the terms should be greater or equal to epsilon by 2. So, taking measure on both sides and using the monotonicity of measure, we have mu of a epsilon is less or equal to mu of collection of all x where mod fn x minus fx is greater or equal to epsilon by 2 plus mu of collection of all x where mod fn x minus gx is greater or equal to epsilon by 2. Now, since fn converges to both f and g in measure, so both the terms on the right hand side tends to 0 as n tends to infinity. So, taking n tends to infinity, we observe that mu of a epsilon is equal to 0, and this is true for any arbitrary epsilon greater than 0. Now, see that collection of all x where f x is not equal to g x, I can write it as union n equal to 1 to infinity a 1 over n, because when f x is not equal to g x, this is equivalent to saying that mod f x minus g x is not equal to 0, and so it should be greater than or equal to some 1 by n, as 1 by n tends to 0. Now, by the above observation, every set of the form a 1 by n has measure 0. So, their countable union also has measure 0, and consequently, we have mu of collection of all x where f x is not equal to g x is equal to 0, and which implies that f equal to g almost everywhere. Now, for a measurable functions f n and f defined over a measurable set D, we will show that if f n converges to f in measure and all the functions f n are greater or equal to 0 almost everywhere, then the limit function will have the same property, that is f is also greater or equal to 0 almost everywhere. From the definition, let E n be the set with mu E n equal to 0 such that f n is greater or equal to 0 on E n complement, because we have assumption that f n is greater or equal to 0 almost everywhere. Now, let us redefine a function g n as f n into chi E n. Now, see that f n is equal to g n almost everywhere, and each g n being the product of two measurable functions is definitely measurable, and further g n is greater or equal to 0 everywhere. Since f n converges to f in measure, it is easy to check that the new sequence g n also converges to f in measure. Now, let epsilon greater than 0 be given. Let A be the set of all those points x where f x is less or equal to minus epsilon. Let us write the set E n is equal to collection of all x belonging to D where mod g n x minus f x is greater or equal to epsilon. Now, see that for x belonging to A, minus epsilon is greater or equal to f x. This is equal to box f x minus g n x plus g n x. So, this is again greater or equal to f x minus g n x, which shows that mod f x minus g n x is also greater or equal to epsilon. Consequently, we see that the point x belongs to the set E n. So, A is a subset of E n for all n. Now, since g n converges to f in measure, so by our definition we already know that mu of E n tends to 0 as n tends to infinity. and hence it follows that mu A should be equal to 0. Now, see that collection of all x belonging to D, where f x is strictly negative, that is f x is less than 0, it can be written as union k equal to 1 to infinity, collection of all x belong to D, where f x is less or equal to 1 by k. Now, we have already seen that each set on the right hand side has measure 0, and so the set x belonging to D, where f x is less than 0, is the countable union of sets of measure 0, and so has also measure 0, and this shows that f should be greater or equal to 0 almost everywhere. We have already seen an example of a sequence of functions f n such that f n converges to a function f in measure, but f n does not converge to any function f pointwise in the whole interval. Now, the question is whether the converse is true, that is whether convergence almost everywhere implies convergence in measure. Now, the answer is again no, but for this example we have to consider some special measure instead of the Lebesgue measure. Though this measure will be formally introduced in chapter 9, just let me tell you very briefly how we can do it. We have seen that the Lebesgue measure is a set function which is non-negative, countably additive with measure of phi equal to 0, which is defined on the collection of all Lebesgue measurable sets, which forms a sigma algebra. Now, in general, if we take a sigma algebra and define a set function, say nu on that sigma algebra, which have all the properties of this Lebesgue measure, that is, it is non-negative, it is countably additive, and the measure of phi is equal to 0, then we say that this is an arbitrary measure defined on that sigma ring. And in particular for this example, we consider the set x equal to capital N, the set of all positive integers, as the sigma ring or sigma algebra. We take the power set of n and we define a measure in this way that the measure of a set of natural numbers is equal to its cardinality. That is, if A is a set of natural numbers which consists of n elements, then its measure is n. If it is an infinite set, then we say that its measure is infinity. This particular measure is called discrete measure or the counting measure, and as I have said that this definition will be formally introduced in chapter 9. Now, let us consider singleton set n for each n belonging to capital N, and let us define f n as characteristic function of singleton set n. See that each f n is then measurable. Now, observe that when we have defined the sequence of functions f n in this particular way, that is f n equal to chi in singleton set n, this sequence of functions f n converges to f everywhere on n, where f x is equal to 0 for all x belonging to capital N, that is f is the constant function 0. But if we take an epsilon 0 less than epsilon less than 1 and we consider the set collection of all x belonging to capital N, where mod f n x minus f x is greater or equal to epsilon, this set is actually equal to singleton set n. But now we are not dealing with Lebesgue measure, we are dealing with another measure which is counting measure, and the singleton set n now has one element. So, its measure is equal to 1. So, mu of singleton set x belonging to capital N, where mod f n x minus f x is greater or equal to epsilon, this is equal to mu of singleton set n, and this is equal to 1 for all n belonging to capital N. And so, mu of this particular set does not tend to 0 as n tends to infinity, and consequently, f n does not converge to f in measure. So, we have seen that in general convergence almost everywhere does not implies convergence in measure. Next, we give a very important result which states that for a sequence of measurable functions f n and a measurable function f defined on a measurable set A of finite Lebesgue measure, if f n converges to f almost everywhere, then f n converges to f in measure also. Observe that in the last example, the set capital N on which the functions are defined is a set of infinite measure. We proceed to prove the assertion in this way. Suppose on the contrary that f n converges to f almost everywhere, but f n does not converge to f in measure. Then what does that mean? There must exist a epsilon greater than 0 for which limit n mu e n is not equal to 0, where we write the set E n as collection of all x belonging to A, where mod f n x minus f x is greater or equal to epsilon. Now, when we have a sequence of non-negative real numbers which is not convergent to 0, this means that there is a subsequence of this sequence which is bounded below by a positive number. So, we can say that there is a delta greater than 0 and a subsequence E n k, belongs to capital N, of the sequence E n n belonging to capital N such that mu of E n k is greater than delta, and this is true for all k belonging to capital N. Let us construct this particular set E as the lim sup k of E n k, which is defined in this way: intersection k equal to 1 to infinity union I is equal to k to infinity E n I. So, what we are doing? We have a sequence of sets E n 1, E n 2, E n 3 dot dot dot, and we are first taking the union of all these sets, then we are taking the union of the sets except the first set, then we are taking the union of the sets except the first two sets, and in this way we get again a sequence of sets which is monotonically decreasing, and we are considering the limit set of that monotonically decreasing sequence of sets. Now, see that since each E n I is measurable, so their countable union is again measurable. So, their intersection, countable intersection is also measurable, and further measure of union I is equal to k to infinity E n I, this is obviously greater or equal to mu of E n k by the monotonicity of Lebesgue measure, and this is greater than delta, and this is true for all k belonging to capital N. And so, mu E is equal to mu of limit over k union I is equal to k to infinity E n I, but this is equal to limit k mu of union I is equal to k to infinity E n I, and since each element is greater than delta, so the limit is also greater or equal to delta. So, I have a set E whose measure is greater or equal to delta, which is strictly positive. Now, since f n converges to f almost everywhere, which means that except for a set of measure 0 at all points, f n x converges to f x, and mu e is a set of positive measure. So, there must exist a point x belonging to E such that f n x converges to f x. But from the construction of the set E, it follows that mod f n k x minus f x should be greater or equal to epsilon for infinitely many indices n k, but this is a contradiction. So, this proves our assertion. So, let us summarize what we did in this module is that mainly we have given an example to show that convergence almost everywhere also does not imply convergence in measure, but if we take a set of finite Lebesgue measure and consider measurable functions defined on that set, then convergence almost everywhere implies convergence in measure. We have also seen some more properties of convergence in measure, and with this we finish this module.